For over a century, theoretical physicists have chased a single quiet ambition: to write down one elegant mathematical framework that perfectly describes every particle and every force in the universe. By the early 20th century, they were making incredible progress. Physicists like Erwin Schrödinger developed equations that successfully mapped the strange, probabilistic behavior of the quantum world. But then they hit a wall. When researchers tried to combine these new quantum rules with James Clerk Maxwell's established laws of electromagnetism, the math completely collapsed. Every calculation they ran returned the same impossible answer: infinity. Calculations return infinity when the math tries to track every possible configuration, as if it were unique. Physicists realized they could resolve these contradictions by identifying redundancies, points where the math says things are changing, but the physical state remains exactly the same. One of those hidden rules is the concept of symmetry. In physics, a global symmetry means that if you take an entire physical system and shift it left or right, or move it forward in time uniformly, the underlying laws governing that system remain exactly the same. This is a foundational assumption of reality. You can rotate an entire laboratory by 90 degrees, and the experiments inside will still yield the exact same results. The math is globally invariant. Then, theorists asked a strange question. What happens if we demand that nature obey a much stricter rule? What if the laws of physics must remain symmetric not just as one big global unit, but independently at every single point in spacetime? Moving from a global symmetry to a local symmetry means you are allowing every coordinate in the universe to change its phase or position completely independently of its neighbors. It is a wildly restrictive demand to place on a mathematical model, and it breaks almost everything we know. To see the damage, we have to look at the math. This equation is a Lagrangian. It is the master blueprint physicists use to configure the dynamics and energy of a physical system, relying on standard derivatives to measure how things change. Now watch what happens when we force our new local symmetry rule onto it. We are telling the equation that it must allow independent phase shifts at every specific point in space and time. The math immediately fails. The derivatives inside the equation can no longer process these erratic local changes. They fail to commute, and the two sides of the Lagrangian fall completely out of balance. Was the mathematics of the system broken? Physicists had to make a choice: abandon the idea of local symmetry entirely, or artificially invent a mathematical band-aid, a new term they could drop into the equation to perfectly absorb all of those local changes and restore balance. They chose the band-aid. They replaced the standard derivative with something called a covariant derivative. This required fabricating a brand new mathematical object, a gauge field, whose sole job was to compensate for the local variations and keep the equation balanced. This was an entirely abstract exercise. When theorists applied this gauge field fix to a specific simple mathematical category known as the U1 symmetry group, they were just playing with numbers to make the Lagrangian work. This fabricated gauge field shared the exact mathematical signature of the physical electromagnetic field. Quantizing this field leads directly to a real-world particle, the photon. The fundamental forces appear here as the universe's mechanical method for preserving local symmetry. Interaction becomes the necessary cost of keeping the internal math balanced. Once theorists realized that demanding a local symmetry generated a real physical force, they began testing this exact same logic on more complex mathematical groups, known as non-abelian symmetries, where the order of operations actually matters. In 1954, physicists Chen-Ning Yang and Robert Mills extended this gauge principle to the SU2 symmetry group. The mathematical output perfectly described the weak nuclear force, which governs radioactive decay. Pushing the logic even further, researchers applied it to the SU3 group. This generated the strong nuclear force, successfully explaining how quarks are bound together inside atomic nuclei through a mechanism called asymptotic freedom. This interlocking radial chart shows how the U1, SU2, and SU3 groups nest together to form the standard model. Together, they output exactly 12 gauge bosons, 1 photon, 3 weak bosons, and 8 gluons that govern almost everything in the known universe. Using nothing but a strict mathematical demand for local symmetry, physics has unified 3 of the 4 fundamental forces into a single cohesive framework. But there is one massive outlier that refuses to neatly fold into this quantum model: gravity, as described by Albert Einstein's theory of general relativity. Einstein's math relies on diffeomorphism invariance, a symmetry that ensures gravity remains the same, regardless of how you choose to label your coordinates. This identifies general relativity as a gauge theory in its own right. The quest for quantum gravity centers on locating the final local symmetry that weaves space, time, and matter into one cohesive, balanced equation.